our last section, which is specifically going to be analyzing and looking at limits. And in particular, section 1.6 is limits involving infinity. Now, there's actually two parts to this. There are part A, which will be, well, let me say it this way. Part A is infinite limits. And part B will be limits at infinity. And those sound very similar, but we're going to make a distinction between those two types. Okay, so we won't get to part B today, so today we're specifically going to be talking about infinite limits. So let's start by looking at an example. Consider the function f of x is equal to 1 over the quantity x minus 1 squared. Now, if you have a calculator, you can go ahead and graph this function, but I'll also draw it up here on the board so that we all know what it looks like. Now, when I go to graph this function, if I didn't have a calculator and I covered up the minus 1 in the bottom, then I would have a picture that looks like 1 over x squared, and the minus 1 shifts it over by 1 unit. And so the picture that I would expect to have is a picture that looks somewhat like a volcano. Very steep and tall volcano, but a volcano. And this dashed line that I have drawn here occurs at x is equal to 1. All right, so here's a picture of our function. Any questions on what that function looks like? Okay. So when I look at this function graphically, the place that's actually kind of interesting in this function is right at the location of x is equal to 1. Everywhere outside of x equal to 1, this is a rational function, and every x value besides x equal to 1 is part of the domain. And so our function is continuous everywhere except at x is equal to 1. So the interesting place on this function is right at x is equal to 1. Now, right when x is equal to 1, our function is undefined. So what we want to do is we want to look at this function near values of x equal to 1 and understand what's happening to the function. So when we talk about looking at values near x equal to 1, we're talking about limits. And so I might ask the question of what happens to our function y equals f of x as x approaches 1 from the left. What's that? Yeah, so as we walk towards x equal to 1, starting on the left-hand side, we're walking towards x equal to 1, and we're looking up at the height of the function. And the closer that our person gets to x equal to 1, the higher the function is getting, the larger the y values are getting. So as x approaches 1, our y values are getting larger and larger and larger. Now remember, when we're talking about getting close to, or when we're talking about limits, what we're talking about is x values getting close to, but not equal to, 1. And so the answer to this question is our function f of x increases without bound. Our y values are getting larger and larger and larger, and there's no stopping those y values. The closer that we walk towards x equal to 1, the larger those y values get. And so the way that we would write that is the limit as x approaches 1 from the left of 1 over x minus 1 squared And then I would write down an equals, and I would say is equal to infinity. And similarly, from the right-hand side, the limit as x approaches 1 from the right-hand side of 1 over x minus 1 squared. Well, as we walk towards x equals 1 from the right-hand side, the y value of our function is also getting increasingly large. Okay, so the closer I get to x equals 1, the larger my y value is getting. Okay, and so our y value is increasing without bound. And so I would write that the limit as x approaches 1 from the right of 1 over x minus 1 squared is equal to infinity. Now, this is okay, but it's a little bit disturbing. Because as we've been talking about limits, we've been talking about x approaching a very specific number, okay, so x approaching a, and the y value of the function approaching a very specific number. And what I've been writing down here is infinity. And as you know, infinity is not a number. So what does infinity mean? Well, infinity is a symbol that's used to describe something that happens without bounds, something that is larger than any real number. And so technically, when I'm looking at this limit, technically, these limits don't exist. Technically, when I write down the infinity, I should really be writing that the limit as x approaches 1 from the left of 1 over x minus 1 squared does not exist, because we're not really approaching a specific y value. But because it's this special case of increasing without bound, then we make an exception to that rule. And so what we're saying here is that saying that the limit as x approaches 1 of f of x equals infinity means as x gets close to 1, f of x gets bigger than any real number we can specify. All right, so again, writing infinity is a special case of limits not existing, but we make an exception because the limit not existing is doing so in a way that we can describe by this infinity symbol. Okay, so let's take a look at another example. All right, on this example, we've got g of x is equal to 1 over x minus 3. All right, so looking at this function, it's a rational function. And the one place where we have a problem is when x is equal to 3. We have a jump or a hole in our graph. And in particular, if I were to graph this function, it would look something like this. We'd have a dashed line at x is equal to 3. And I'd have two branches, similar to what I have over there, except for one branch, the left-hand branch, rather than pointing upwards, is pointing downwards. And so on this particular example, if I'm standing on the x-axis, and I'm walking towards an x value of 3, that's our interesting x value on this example. As I'm walking towards x equal to 3, the y values are getting larger and larger and larger, but they're getting larger in a negative fashion. And so here I would say that the limit as x approaches 3 from the left of 1 over x minus 3 is equal to negative infinity. But approaching from the right-hand side, we've got the limit as x approaches 3 from the right of 1 over x minus 3. Well, approaching from the right, our y values are getting larger and larger in a positive direction. So that's equal to positive infinity. at this point, you're actually ready in your mathematical career to hear a definition of a word that you've been using for at least 2 full semesters. And it turns out that you've been using this word without a real definition because you need to talk about limits to give the definition here. And the definition is the definition of these vertical dashed lines. And so you all know that all these vertical lines, they're all vertical asymptotes. Okay? So let's write down what it really means to be a vertical asymptote. A vertical asymptote we say that the line x equal to a is called a vertical asymptote of the curve y equals f of x if at least one of the following is true. Either the limit as x approaches a from the left of f of x is equal to infinity, or the limit as x approaches a from the left of f of x is equal to negative infinity, or the limit as x approaches a from the right of f of x is equal to plus or minus infinity. Okay, so we have a vertical asymptote as long as our x value is approaching a, in our second example, a is 3, as long as our limit as x approaches 3 from either the left or from the right is equal to either positive infinity or negative infinity, then we get a vertical asymptote. So you've seen pictures of vertical asymptotes ever since college algebra, but now you've got a definition for them. All right, so here are our examples. Here we've got a vertical asymptote here, this guy. And a vertical asymptote at x is equal to 1 because the limit as x approaches 1 from the left of 1 over x minus 1 squared is equal to infinity. Also because the limit from the right is equal to infinity. And our example over here, we have a vertical asymptote at x is equal to 3. All right, so here's the question that I would like to leave you with. And so this is something to think about. After I leave this question up on the board, I'm going to write down a few practice problems, and we'll start class next time with a discussion of this question. Can a function y equals f of x be defined on a vertical asymptote? Both of our examples that I gave you here, in both of these examples, our function is undefined at the place where we have a vertical asymptote. Okay. X equals 1, x equals 3 in the other example. So is it possible to have a function where the function has a vertical asymptote, but yet the function is defined along that vertical asymptote? So that's a question to think about for next class, and we'll discuss that at the beginning. All right, any questions about what I'm asking? Okay.